Hello everyone and welcome back to my YouTube channel. In today's video we are going to see how we can use surface integrals to evaluate area. Before we start, I want you to recall that in double integration, area of a region R can be evaluated as double integration of 1 dA over R. So far in the earlier videos, we have seen surface integrals of scalar fields as well as vector fields. So to recall, let me just state over here the formula for surface integral of a vector field f over a surface S. It is denoted as this and it is evaluated as the double integral over T f applied on the parameterization of the surface S given by say gamma of u v multiplied by the norm of the fundamental vector product or the normal. And then here we will have either du dv or we can also have dv du depending on the type of region. T is going to be in the xy plane. Now moving forward, we are going to utilize this formula to develop a formula for area using surface integrals. So by that we can say that area of a surface S in R3 can be given as surface integral of the scalar field. Instead of f we are going to write down 1 ds, and this changes to double integral over t. Now since the scalar field is 1, so the image of f applied on gamma uv being a constant is also going to be 1 multiplied by the norm of the fundamental vector product, and then we could have the order of integration as du dv or dv du, and this simplifies to double integral over t norm of gamma u cross gamma v and then du dv. Let's get ahead and see an example for this. So let's say I want to calculate the area of the surface of cylinder given by x square plus y square equals to 3 from z equal to 1 to z equal to 3. Before we move forward, let us see the diagram for this. So since we are given that the cylinder is x square plus y square equals to 3, let me make a change over here. Let me say it is 3 square or 9. So if this is the surface of the cylinder, then it would be moving along the z axis. So if this happens to be the xyz space, then we have a circle of radius 3 in the xy plane, and this circle moves indefinitely up and down, giving rise to a cylinder. Now also note that we are given a bound for z, so z ranges from 0 up to 3. So the base of the circle is in the plane z equals to 0 or the xy plane, and the top of the cylinder is cut at the z equal to 3 plane. So it is 3 units parallel to the xy plane on the positive z side, and the surface of the cylinder is this patch. So we have a curved surface which makes up the cylinder, and we wish to find out the area of this. Now if you recall in your lower classes, you might have done the surface area of cylinders. So here we are interested in knowing the curved surface area of the cylinder, and that is given as, so now then since this cylinder is formed by stacking circles of radius 3 on top of the other, so that's going to be the circumference, and the circumference of the circle is given by 2 pi times the radius, which is 3. So this is the circumference of the base circle multiplied by the height. So we are moving it from z equal to 0 up to z equal to 3. So the height is effectively 3, and this gives us, it is going to be 18 pi square units. So we already have an answer. Let's just quickly give it a check and use the formula of surface integrals and verify. To begin with the solution part, we got to parameterize the surface S. So first of all, let me say that let S be the surface of the cylinder given by x square plus y square equal to 3 square, and between z equal to 0 to z equal to 3. Now going ahead, we will be first parameterizing s. So we parameterize s by, say, gamma. Now, of course, since it is circular in nature, we might think of a polar coordinate. So we will be saying that, let x be r cos theta and y be r sin theta. And when you substitute this in the given equation of surface of the cylinder over here, so we will be getting that r square cos square theta plus r square sin square theta is equal to 9, and this gives us that r square is equal to 9, and ignoring the negative part, since it's a distance, we get that r is equal to 3. So when we parameterize gamma in the form of r and theta, so please note that we will not have r, instead we will have 3 cos theta for x and 3 sin theta for y. So one of our parameter is theta, so I will say x is equal to 3 cos theta and y is equal to 3 sin theta. Now the second parameter which is going to be there will develop from here, z equal to 0 up to z equal to 3. Since a circle varies between these two planes, so my second parameter is going to be z, and of course z takes the value as z. Now moving forward, we got to give the limits of both the parameters. So we'll say that where theta z belong to t, and theta is going to range between 0 up to 2 pi, since we have a complete circular disk, multiplied by the range of z is given from 0 up to 3. So we have it ready. Now just have a look at the formula again. So we will be needing the fundamental vector product followed by its norm, and then we'll be ready to integrate. So let's go ahead and evaluate the fundamental vector product. So for that, I will need the partial derivative of gamma with respect to theta, and that is going to be minus 3 times of sin theta, 3 times of cos theta. Since z equals z, it is independent of theta, this is going to be 0. Whereas gamma partial derivative with z is going to be 0, 0, 1. Taking the cross product, we will get gamma theta cross gamma z, and that is evaluated as the determinant I, j, k as the first row, the second row being negative 3 sin theta, 3 cos theta, 0, and the third row being 0, 0, 1. So for the I component, we are going to have 3 cos theta minus j component, we'll have negative 3 sin theta, and the k component will be 0. So thus we have the normal or the fundamental vector product to be 3 cos theta, 3 sin theta, 0. Now I want you to make a note over here that since the surface is perpendicular to the xy plane, so if you happen to draw any normal, the normal will be lying parallel to the xy plane. So anything in the xy plane will have the z component 0, and that is what exactly we are getting over here. So moving on further, we need the norm of this. So the norm is going to be square root of 9 cos square theta plus 9 sin square theta plus 0 square, and that's going to return us the value 3. Now we are on to the final step, so let's get started here. Area of S, we are not stating the formula, we are directly moving on to the next segment, substituting the values. So let's say I decide that the order of integration is going to be d theta dz. So for z, the limits are from 0 up to 3, and for theta, the limits are from 0 up to 2 pi, whereas the norm of the fundamental vector product is 3. So you see that it's a constant. So integrating d theta, we are going to get 2 pi, whereas integrating z, we are going to get 3. And when we complete this, we will be getting 18 pi square units. And this is purely in alignment with what we have discussed earlier with the help of formula. So you can check over here, we have got 18 pi square units. So also we have a nice corollary to this for surfaces which are expressed as a function of x and y. Let me just state that and we will see one more problem based on that. So if we have a surface S which is given by z equal to f of xy, then in this case the area of S is as simple as double integral over t square root of 1 plus fx square plus fy square and then dA, where dA will be either dx dy or dy dx. And the proof of this is very simple. So since S is surface, S is given by z equals to f of xy, we can parameterize S by gamma of xy, where x takes the value x, y takes the value y, and since we have z expressed in f of xy, I can say that z takes this. And moving forward, the partial derivative of gamma with respect is going to be 1, 0, and here we will get the partial derivative of f with respect to x. And likewise, gamma partial derivative with respect to y, we are going to get 0, 1, and f partial y. And the normal is going to be the cross product of these two, and that we have seen is evaluated as I, j, k in the first row, span 0 fx followed by 0, 1, fy. So this is going to be I hat minus f partial x minus j hat f partial y plus k hat into 1. And so this is equal to minus fx minus fy comma 1. The norm of this is going to be fx square plus fy square plus 1 square, and that's going to be inside the square root. And therefore, by the formula of areas using surface integral, this is going to be double integral over t, and since this is the norm, we will be having 1 plus fx square plus fy square dA. So here we have a problem. Find the surface area of S represented by the following surfaces, and it is given that S is the surface of the paraboloid. This is the equation which is cut by the plane z equals to negative t. So first let us just see how the graph is going to look. So if this happens to be the xyz space, we have a parabola whose means where the constant is 1, that means 0, 0, 1 is a point on the parabola. And if we will look that we have the parabola negative x square minus y square, so that's an inverted parabola with respect to the xy plane. So we have a parabola which goes down like this. This is the back side and this is the front part. Now further, this is cut by the plane z equal to negative 3. So we are going to go down the negative z axis also to z equals to minus 3, and this is where we expect the parabola to be cut. So that's what we have. And if you will look at from the top, means you're going to see a circular disc which will be looking like this. This is going to be the largest disc. And we are going to use the formula which we just derived for one reason, that you can see that the surface z is expressed as a function of x and y. So here we have z is equal to f of x comma y, which is equal to 1 minus x square minus y square. So this thing makes the evaluation part very simple. So we are going to say that area of S is going to be double integral over t. We'll state that in a while later. 1 plus the partial derivative of f with respect to x is going to be negative 2x, and f partial derivative with respect to y is going to be negative 2y. So this is going to be 1 plus negative 2x square plus negative 2y square, and then of course here we can have either dy dx or dx dy. For time being, I'm just putting the element as dl. And here we have the region T. The region T is the projection of our surface in the xy plane. So for the projection part, we are going to look at our surface from the positive z axis, and once you are standing right over here and you happen to look down, what you are going to see is this plane, this circular disk. The surface which is attained over here is the intersection of z equals to 1 minus x square minus y square, the paraboloid, and the plane z equals to negative 3. So if we happen to solve these simultaneously, we are going to get negative 3 is equal to 1 minus x square minus y square. That gives us x square plus y square is equal to 4 or 2 square. Thus, this circular disk which you see has the radius 2. So plotting that in the xy plane, we will be having a circle of, we will have a circular disk of radius 2. And we are very well aware that if it is a circular disk, then we can resort to the usage of polar coordinates. So before heading on to that, let me say that this is going to be double integral over t 1 plus 4x square plus 4y square dA. And now since we are going to switch to polar coordinates, dA is going to become r dr d theta, where r is the Jacobian of the transformation. The limits of theta is from 0 up to 2 pi. That is evident from here since we have a complete circle. Whereas the limits of r is going to be from 0 up to 2. And over here, from the term 4x square plus 4y square, we can take 4 out and we'll be left out with x square plus y square. And that in polar coordinates is equal to r square. So the entire equation reduces to a simple double integral, which is given by this. Now for the last part, I want you to solve the double integral by yourself and comment down your answers, and we'll be checking whether it is right or incorrect. So in the successive video, we are going to talk about Stokes' theorem followed by divergence theorem. I hope this video helps you in understanding the various applications of surface integrals, and one which we have discussed here is finding area of surfaces. Thank you so much and happy learning.